Should be recording.
Cool. So hi, we're CAIS++, the undergraduate branch of USC's Center for AI and Society. Thanks so much for coming out today to our virtual showcase. We're a group of about 150 students driven to promote AI for social good. And this can be seen in every aspect of the 3 pillars of our mission on this slide. So each semester, we welcome a new cohort of students and teach them an AI curriculum with the focus on machine learning that we designed. As of this semester, all our lectures and notebooks are publicly available on our website. And we also have a YouTube channel, so really to democratize the education and resources. Our members then work in teams that collaborate with professors, startups, and community organizations to tackle pressing societal problems with AI. We also host regularly events to spread awareness about AI for social good to the USC community. And so that's pretty much what our club does. And I'm going to hand it off to Ted, our VP of projects, to talk more about the projects overall, as well as the projects this semester.
Hey, so yeah, over the past 3 years, we've completed about 36 total projects that develop machine learning approaches to tackle meaningful and real world societal problems. But this semester, even with COVID, we're really excited to have 3 of our project groups present their work, and 1 group, which has a bunch of CAIS++ members in it, present as well. They're from the USC CS 499 class, which is called AI for Sustainability, and pretty much is doing the same thing as CAIS, but for class credit. How it's going to work is each group is going to has already pre-recorded their presentations, and we're just going to play them. After each presentation, we're going to have a few minutes to ask questions and sort of interact with the people from that group, just like an in-person showcase. So type your questions in the chat, and I'll be keeping an eye on it so we can ask them the questions. I don't think we're going to be able to get to all of them, unfortunately, probably just 1 or 2, but we'll be sure to share information about the people on the team. So if you really have a deeper question about it, we can put you in contact with them and they can answer it. The way it's going to work is we're going to have 2 presentations first. We're going to have a short 3-minute intermission, and then we're going to have the final 2 presentations. And I believe the first one today is genomics.
Yeah, I'll stop sharing quickly and then I'll bring up the genomics presentation. All right, people should be able to hear.
We're the Viral Mutations Project team, and here's how we're predicting the next pandemic through viral mutations. As many of you can probably tell, viral pandemics are incredibly complicated, unpredictable, and difficult to control. In the coming years, epidemiologists and virologists are predicting a much higher number of pandemic-level viruses mutating, mainly due to climate change. And because of climate change, these hotter temperatures mean more tropical climates for mosquitoes to thrive in and spread disease within. As some of these environments become more livable and as humans encroach upon animal habitats, there are more instances and opportunities for cross-species viral transmission to occur, as well as with the constant increase in human population, overcrowding and higher population densities occurring are going to further ease the spread of pathogens. In addition to all this, with this higher number of natural disasters that are occurring, temporary high population density of populations that would not normally be in the same place is going to happen fairly often. So for instance, when people are all evacuated for a fire or an earthquake, etc. We chose to focus our project on influenza A. And you may be wondering why we chose to look at the flu rather than at the coronavirus, but we do have some valid reasons. The avian flu is actually categorized by the World Health Organization as a virus of special concern. Similar to the coronavirus, the influenza has an RNA genome, meaning that it mutates incredibly rapidly. The flu that already goes around every year causes a high number of deaths and is transmitted very easily between people. They're predicting that in the coming years, a new, more virulent strain of the influenza will develop and will be more deadly than COVID. Some researchers have even predicted a 40% or higher mortality rate. So by predicting these possible genomic mutations that we're looking for, we're hoping to find virus strains that will infect humans and could lead another possible pandemic, just so we have a better idea of what the future might look like and can start pandemic prevention a little further before it hits. So we began this project lecturing our group members about some significant biological concepts which come into play along the lines of virulence and genomic mutations. So a couple of these important concepts that I'm going to explain to you are K-mers and epitopes. A K-mer is this subsequence of a genome of length K. So for instance, one mer would be a single base pair, so just the letter A, T, C, G, or U. And as you can kind of see in this image, a 3-mer would be something like TGG or ATG. So these K-mers allow you to capture and encode genetic information in a machine learning friendly way by counting the number of occurrences of each subsequence, instead of having to look at the genome as one long string. Another key term is an epitope. So an epitope is a small protein segment which allows for viruses to attach themselves to and infect cells. These epitopes are typically made of about 5 to 6 amino acids, so about 18 base pairs code for them. By looking at the sequence of amino acids instead of at the genome itself, we're able to abstract a lot of the unnecessary information away and decrease the computational load of our data.
A little bit about the data that we're using. So the data that we're using includes whole genome sequences, segment 4 sequences, and epitope data from the NCBI virus database and from the influenza research database. When we first started our research, we looked just at whole genome sequences of influenza A. However, influenza A viruses have a segmented genome, and some segments matter more than others when it comes to deadliness and infectivity. In these segments, segment 4 of the influenza genome is particularly important and well studied, and that's because it codes for the protein hemagglutinin, which is an important factor in viral infectivity. As mentioned before by Shannon, amino acid sequences are much easier to work with than genome sequences, as it abstracts away a lot of the unnecessary information. So we looked into these 3 data sets, and so these were collected through FASTA files. We ran them through a Python script, and then we had these various data frames for whole genome, epitope, and K-mer. And yeah, this is an outline of our pipeline for data processing. And these are the results of our K-mer classification. So we ran these classifying methods on around 5,000 genome K-mer counts. And then these were mainly to look at accuracy, since our data set has approximately a 50-50 split for both human and non-human transmissible viruses. And as you can see, these are pretty accurate. And as for our segment 4 classification using this method, it was similar, but slightly worse due to the relatively short length of viral RNA.
So the next thing we did is we used some of the same methods on epitopes. So here are some of the results from running classifiers as well as a neural network on around 3,000 epitope amino acid sequences to predict if a virus caused a positive test in humans. And again, we looked at accuracy here because our data set had around a 50-50 split. So accuracy was a good first look at how the models were doing. And again, here, random forest was the best performing model. But as you can see, the accuracy here is much lower at around a 75% level. And our initial tests with GAN-like architectures did not produce great results, but we think that with better information encoding and through fine-tuning the model, we should be able to improve those results greatly. Thank you so much for listening to our presentation. Please let us know if you have any questions or comments. And again, this is a work in progress, so definitely also check in next semester for new updates and details.
Okay, so I'm Shannon. I'm one of the project leads. If there are any questions, please feel free to type them in the chat, and Lena and Ted will field them to me.
I have a question. If someone else does, definitely like ask theirs first. But so I think you mentioned at the end that you're planning on like making a GAN, but what was your more specific plan for that?
Yeah, so our plan is to make a GAN to help us determine what characteristics in the genome are particularly relevant in human-to-human viral transmission. And so once we have some new sequences that we predict will infect humans or are at a high likelihood to infect humans, our plan is to run them through some protein folding software because each genome just codes for a bunch of amino acids. Once we have those amino acids laid out, we can create this protein that the virus will likely use to infect other cells and other organisms. And once we have that, that can then be used for further like vaccine research to try and create something to combat those specific proteins.
To add to that, because what we're trying to do is we're trying to essentially see how many like mutations it would take for a virus to be able to infect humans. I said GAN mostly as a kind of bridge to what most people know, but essentially we're trying to generate sequences and essentially perturb the virus sequences to be able to see if it'll be able to infect humans. So GAN, essentially.
Yeah, looking at the chat, I think Zane might have had pretty much the same question about the GAN. Was that your question, Zane, pretty much?
Yeah, it's pretty much the exact same question.
Great. If anyone has any more questions, definitely feel free to reach out to Shannon and Laura or like ask in the chat. And we can probably move on because we're kind of short on time. So move on to the next presentation.
Hi, everyone. I'm Andrew, and I'm joined here today by my amazing and talented teammates, Lena, Nicole, and Jay. And we're extremely excited to talk to you all about our topic, which is predicting K-12 school performance in California based on school funding and regional socioeconomic factors. So our problem statement is as follows. Pervasive and persistent achievement gaps exist across K-12 schools in California. And they're often correlated with demographic, socioeconomic, geographic, and school-related characteristics. In addition, funding is typically not equally distributed among different school districts. And within the realm of education policy, there is no consensus on how much funding contributes to achievement. And so we wanted to look into this further by first analyzing how school funding is allocated. In most states, including California, they use the foundation grant system, and that works as follows. Each state sets a minimum amount of funding for each student. So for example, $11,000, which districts are supposed to provide. Whatever they can't provide, states are supposed to fill in that gap. So if the district can only afford $1,000 per student, the state comes in and spends another $10,000 to reach that threshold of $11,000. Once that funding has been allocated for each student, districts are able to add a 1 to 1.4% property tax on properties within that district. And so if you have an area that is extremely wealthy or has a high property value, they will generate much more property tax income. And you see that this discrepancy from school district to school district widens. So our primary objective in our research is to develop and leverage ML models to identify features predictive of K-12 school performance and to inform the design of state education policy and initiatives. And now I'm going to hand it off to Nicole to talk about how we collected our data.
Awesome. Thank you, Andrew. So in terms of our data, if we go to the next slide, we'll see that we got our data from 3 different sources. First, we have students' math and reading performance scores, which we get from the annual performance data. Next, we have school funding data, so we know how much funding each school has gotten from the local to the state to the federal to the levels. And then there's also a total revenue that they get from all 3 of those areas. And we also have housing and census data from Social Explorer at a census tract level. So we did some exploratory data analysis to understand our data set better. First, we see in the relationship between median income of an area and the local funding that a student has, we see that the higher the income, the higher the local funding that they get at the bottom right graph, which means from property taxes, school tuition, other kinds of local fees. The inverse is true for state and federal funding, leading to a more equal amount of total funding that we see at the top left graph. So this data supports our understanding of how the foundation grant system works, as Andrew was explaining. And we also found that the higher local funding quartiles also have higher median school performance. So this relationship is true only for local revenue, not true for federal, state, or total revenue. So we see that there's some local characteristic of like socioeconomic status or property taxes or something else that's contributing to this kind of relationship. And in terms of school performance, here are graphs of primary, middle, and high schools, math and reading performances. As you can tell, the distribution is pretty significantly different. So this informs how we choose to split our data frame by school level when we perform modeling, which Lena is going to talk about now.
The problem of predicting school performance was formulated as a machine learning regression task to predict two labels: the percentage of students in each school that were proficient in mathematics and the percentage proficient in reading per the state standardized tests. The following primary metrics were computed across 5 cross-validation folds for each model: the R-square score, which is the proportion of variance explained by the model, and the mean absolute error, which is the average of the absolute values of the errors. In our case, this refers to how far off the predictions were about proficiency level on average. We experimented with 9 different types of linear and nonlinear regression models, which are listed on the next slide. For sake of time, I won't read them off, but they're here for reference. This slide shows some of our results from predicting mathematics performance for all schools. XGBoost was the highest performing model, achieving an R-squared of 0.67 for predicting the math performance of all schools, and a mean absolute error of 9.16. It's also worth noting that XGBoost performed better in individualized models that predicted school performance by level, with an R-squared of 0.75 for middle schools and 0.73 for primary schools. That's an interesting amount of variance to be explained by the model with these features. This next slide shows our results from predicting the reading performance for all schools. Again, XGBoost was the highest performing model for all types of schools, achieving an R-squared of 0.64. And it's also worth noting that XGBoost performed better in models that predicted school performance by level, with an R-squared of 0.74 for both middle schools and primary schools. This next slide talks about has the important features from the XGBoost model. I won't go into too much detail because time is short, but per permutation and feature importance, the proportion of students receiving free or reduced price lunch were the most important features for both predicting math and reading proficiency. In fact, the model just using those 2 features alone achieved an R-squared of 0.62 and 0.6 for math and reading respectively. So those 2 explain quite a bit of the variance. Different funding features highlighted in purple were important, as well as other population-related features. For example, the proportion of adults in the area with college education. And these all contribute to a student's personal, social, and cultural capital, which influence performance. Our future steps are to obtain and incorporate additional data sets to inform the modeling, for example, publicly available property tax information. And since we have a better idea now of what types of community factors contribute to performance, I'd like to frame an optimization problem to design community interventions that can maximize performance. We also are going to make our GitHub repository public to facilitate more collaboration. And we also have a website, which is now actually live. And there's a screenshot of the website on this page. Everyone should visit it. We'll put the link in the chat. And we'd like to thank our wonderful advisor, Bistra Dilkina. Her picture's in the top right of this set of pictures. And yeah, thank you so much for listening to our presentation. And we really would love to hear any questions or comments.
I have a quick question. Can you talk a little bit more about the class and sort of like the requirements if you're a CS student to sort of get into it, because I mean, this is a really cool project, and if I wasn't a graduating senior, I definitely think I'd be considering it.
Sure. So yeah, it's a 4-unit tech collective, and it's taught by Bishra Dilkina. As I'm sure a lot of you know, she's the co-director of CAIS. And so she's technically our faculty advisor for all of our projects in CAIS++. And in order to sign up, I believe you have to get D-clearance from her. And she has a Google form which she sends out every semester. Yeah, I'm not really sure when her class will be, but definitely if you want a tech collective for CS, then definitely sign up, because it's a way to basically do a CAIS++ project while getting credit for it. We do actually learn stuff in the class too. It's not just the project, but everything is applicable to the project. So there'll be a week on the classification, week on regression, week on ML fairness.
I also have a question. You guys were talking about expanding your data set or looking for collaboration, and kind of with that scope, are there any features that you guys will be looking out for to try and add to your data set, which you believe would help your classification?
Yeah, so one thing we were thinking of, so apart from the property tax information, because that could be very helpful, because that would definitely correlate with how much local funding schools are receiving. But we're thinking of looking at satellite information, because there's a lot of projects that use geospatial data to predict social characteristics, and using geospatial data to predict educational performance could also uncover some more factors. For example, a lot of rural schools don't perform as well as urban schools, but then of course, if it's an inner city school, it's not performing as well as other schools. So being able to disentangle some of the social and then cultural and geographical factors with additional data from geospatial could be interesting.
Hello, we are USC's Project X team in the year of 2020. This is a 3-month machine learning competition where competing schools conduct original research to tackle some aspect of climate change. Each of my awesome teammates will briefly explain their unique contributions, and all slides will be accompanied by some sort of takeaway. If there are any questions, we'll be happy to answer them at the end.
Hello, my name is Nicholas. I'm a co-lead in the Project X team. So we're participating in this climate change competition, and we decided to look at variable renewable energy and the power grid. So because these sources like solar and wind have unpredictable output, we study how the rate of power that comes from these sources affects the number of times you have to activate balancing mechanisms in the power grid, which incur costs in operations and management.
My name's Thomas, and in the preliminary stages of this project, my work focused on studying the existing literature on predicting energy production from renewable sources. I dedicated time to analyzing and comparing the existing ML models that have been previously used on similar data to our project so as to establish a foundation for our research. After we were set on a problem, my work focused on data extraction and pre-processing in preparation for model building. Because for this research paper we are working to build on the work presented by Aidan O'Sullivan and his co-authors, we needed to better understand the platform they used for data extraction, namely the Elexon portal. Elexon is a company that tracks energy generation of all fuel types in Great Britain, and it provides generation data in 30-minute intervals. The paper we were building off also extracted data from Elexon, but they then aggregated the observations into daily and weekly intervals. Because we wanted to study predictive models in shorter time periods, such as an hour or a few hours, we needed to recollect the raw data and manipulate it as deemed appropriate with the 30-minute observation intervals.
We queried our data from Elexon, and the data frame we use in our model refers to the aggregations of generators across Great Britain at 30-minute time intervals. Our data mainly includes our calculations from the data that we queried. The variables in this data frame are total energy output, number of severe ramping events, load factor, total VRE generation, and the VRE factor of the total energy produced at given timestamps. Doing some analysis of our data, we found that the average load factor contains a lot of seasonality at yearly periods and shows a downward trend. And while the number of startups and ramping events also seem to have seasonality, they seem to have a slight upward trend.
This is Christopher Fucci. I'm part of the modeling team at Project X, and my specific role was to explore different models and how well they predicted our data, and to write up the results for our paper. So as of right now, I've explored sequential and transformer models. I'm hoping to further explore transformer models as our initial results were pretty poor, and it was likely due to the fact that it was a fairly simple model that was unable to understand the complexity and variation in our data. Furthermore, I'm also hoping to explore CNN models, as we've had great results with Jaresh's first model that was fairly simple. He specifically tried LSTMs, sequential models, and convolutional neural networks alongside dense layers. So within his models, he received very good results for dense layers and specifically convolutional neural networks. However, like myself, his LSTM and sequential model performed very poorly. It was likely due to the fact that they were fairly simple models and they just weren't able to capture the complexity and variation in the data. But the CNN model and the dense layer model were fairly simple as well, and they had great initial results. So we're hoping to further explore them, especially the CNN, as it was able to capture much more of the complexity and the volatility of the data. Furthermore, both him and I are hoping to explore LSTMs and specifically transformers because we think that they can perform better, and it was just the fact that it was a simple architectural model that made it perform poorly. And if we gave it something more complex, it would be able to capture the complexity in the data. Thank you.
All right, cool. I think we have some members from that team here. So if you want to ask any questions, we can have a couple right now. I had one question, just more about the competition, but when is the deadline for this research project? Because I know originally it was, I think, early December, but was that moved out?
Yeah, so as you can see, we don't have quite a polished end product yet because the competition's not over, but we're gonna keep on working on it and building off of what we presented today in terms of modeling and benchmarking our results with previous work. And that should be done by the end of November, early December, when the competition's all over. And the end format is going to be just a research paper we're going to submit.
Cool. And then I had another quick question, just more out of interest, but I know Chris talked about using transformers, but I was wondering if you could elaborate a bit more on why you'd prefer a transformer model or trying that out versus another model for your specific problem.
So I think at the start we were mostly brainstorming possible architectures that could help us. I think transformers is just some idea we're trying out and seeing if it sticks, you know. I think mostly because of its use in NLP, which is also a time-dependent domain. So we were thinking maybe we could have some advantage using that sort of new model. So that's very exploratory. Like realistically, we would stick with trying more classical approaches to this problem, like LSTMs, like making sure that works. And also there are some pretty promising results with CNN architectures. So you're doing like a rolling window of X number of days and feeding that sequential input into an LSTM. I think that would work pretty well. So that's kind of where we're at.
Cool. So I can't really, I guess, see any more questions in the chat. So we can, I guess, we're going to finish this showcase really quickly. We can move on to ML fairness.
Hi, we're the ML fairness team. I'm Nico.
I'm Ratika.
I'm Brittany.
I'm Natalie.
And I'm Sam. Mingtao couldn't join us today. All right, so let's begin with an example of the problem that we're trying to address. A couple years ago, Amazon discontinued the use of their machine learning recruitment software after realizing it was implicitly biased against women. Because most of their training data consisted of male applicants, the software learned to penalize resumes that included words closely associated with women. However, even after trying to remedy this issue by removing explicitly gendered words, their models still continue to carry an implicit gender bias. However, this problem is far from unique to Amazon. The industry right now is trending towards using machine learning recruitment software like Amazon did to scan resumes. So it's important now more than ever before to ensure that these softwares are not biased towards any specific group or individual. Extrapolating from this Amazon example, our project aims to address the question of how we can reduce gender bias when filtering resumes. So the first step to do this is trying to get a numerical representation of the words that we're trying to compare. And how do we do this? We do this by creating a word embedding. Word embeddings are the first step towards training natural language processing models. They are used to convert words into numerical representations that allow machines to understand their textual information and allow words to be compared to each other in a numerical way. The encoding of a word should take into account all of its context, underlying semantics, as well as its interrelationships with neighboring words. In this example, we can see the word embeddings as feature vectors, allowing us to visualize the relationships between words king, man, woman, and queen. This allows us to encode similarities and differences in multiple dimensions, capturing complex relationships between.
We used two different data sets in our research. The first one consisted of 2,000 resumes from GitHub in the formats of a PDF, doc, and docs format. The resumes had varying formats and classifying information. The second data set consisted of 50,000 tweets from Trump before the election. We measured bias using cosine similarity, REPA scores, and a resume ranker. The resume word embedding had a slight bias towards the word women, and Trump's tweets had a bias toward the word woman, even when using gender-neutral language. Here's a quick illustration of cosine similarity. It helps resolve some of the pitfalls that are brought from using Euclidean distances as measurement of similarity. Euclidean distances are unbounded and would take extra computation to normalize, while cosine similarity is bounded between -1 and 1. Additionally, two vectors with the same direction but different magnitudes are analogous to having a textbook about an idea and an essay on the same idea. One might be much larger than the other, but they are still about the same thing and are therefore similar. A Euclidean measurement would mark these as different, but cosine similarity marks them as similar.
The key algorithm that we use in our project is hard debiasing. Hard debiasing reduces gender bias in word embeddings by essentially removing the gendered component from the embeddings of given biased words. The algorithm's success can be measured by calculating the clustering accuracy, or the ability to cluster words in such a way that the clusters correspond with each gender. If the algorithm successfully removes bias, the clustering accuracy will be low. So in the example image above, it would be much easier to distinguish a cluster containing game, brilliant, and programmer in the first distribution than in the second. However, hard debiasing has some shortcomings. For one, the word embedding space can contain information about the word frequency that distorts the calculation of the gender direction. Double hard debiasing builds on hard debiasing. Words are first projected into a frequency-free subspace before running the hard debiasing algorithm in the previous slide. As seen in the example, the double hard debiasing more successfully removes gender bias by including the frequency mitigation step. This is the debiasing method we ended up using to debias our data. Above is the accuracy result of debiasing our two data sets. As described before, the accuracy is based on the ability to cluster together similarly biased words. If the words that contain strong gender bias are still near each other in the biased embedding space, the clustering accuracy will be high. So lower accuracy is better, and an accuracy of 0.5 represents random clustering, which indicates that the data is unbiased.
Additionally, we also measured the results using the cosine similarity method described earlier. As seen in the left graph, the gender-neutral words are now evenly spaced between the women and men sets, and therefore that represents that the words are no longer biased toward either direction. Additionally, if you look at the right, you'll see that the graph of our embedding is still structurally similar to the one before, which means that the structural semantic features were still retained. When trying to debias the Trump dataset, we ran into some issues. However, we did, through the process of trying to fix this, we did find some cool insights into his dataset. As seen on the right side, the the clustering is a lot smaller than the resume data set. And we initially thought this was due to overfitting. So we tried to reduce the dimension size of the word vectors to see if we could underfit it. However, this didn't change the cluster size. So ultimately, we concluded that the reason why Trump's embedding is a lot more clustered in one area is because Trump is very repetitive in his language and his style. Meanwhile, the resume data set contains 2,000 different resumes written by 2,000 different people who all have different styles. So that was an interesting bit. Additionally, we tried to measure the debiasing through a method called REPA, which I'll explain quickly. It's basically projecting a word onto a gendered relationship vector. So in this case, man minus woman would be the gendered relationship vector. And then you'd project a word like leader onto that vector and then get the magnitude of that projection to represent the skew. So if it's positive, then it's leaning towards the male side. If it's negative, it's leaning towards the women's side. We did this calculation on all the neutral words in our embedding and found that before debiasing, it had a spread of around negative 1.5 to 1.5, which is bad because we want it to be tightly bound around 0. And then after the debiasing, it had a spread of around negative 0.7 to 0.7, which is a big improvement.
All right, so while we had a lot of success with double hard debiasing, we also attempted to use different types of debiasing techniques to reduce bias in our data sets. And one of the most popular ways to do this in ML is through adversarial learning. And so here is kind of how it works. Let's pretend Z is a sensitive attribute that we want to prevent our algorithm from discriminating on. For example, age or race, and in our case, gender. It's insufficient to just remove Z from the training data because it's usually correlated with other features. And what we really want anyways is to prevent our model from learning a representation that relies on Z in any substantial way. And to this end, we train our model to simultaneously predict a label Y and prevent a jointly trained adversary for predicting Z. If our model produces a representation of X, which is our original data, that encodes information about Z, an adversarial model could easily recover that info and accurately predict Z for all X using that representation. Oppositely, if the adversarial model fails to pick up on any information about Z from a representation of X, then that representation is no longer dependent on Z. We can think of a model as multi-headed, with one head for predicting Y and another for predicting Z. Now consider G to be the shared learned representation of the input. Our ultimate goal is to get an optimal G that still predicts Y, but can't really predict Z. So every time the shared representation still allows the model to predict Z, we send back a negative signal to the shared representation using a negative gradient. And we do that constantly until we can predict Y and no longer predict Z. So that's what it is in ML, but let's think about it in terms of our NLP model. So adversarial learning in NLP is actually quite new. And it's a little bit more difficult to implement because traditional adversarial learning models depend on using specific attributes as a predictive attribute and a protected attribute. And so we tried to use an adversarial model for our project to train word embeddings by attempting to modify existing code, but it's more difficult than we anticipated. So future steps for success would include finding models with access to their training data, and looking at newer publications and programs that have recently come out about adversarial learning.
Thank you for your time. Are there any questions?
I've got a quick question. What was your reasoning behind looking at both the debiasing of all these resumes and then Donald Trump's tweets? Like, how did you kind of bring all this together for one overall conclusion kind of thing?
So yeah, for the resume data set, it was somewhat limited. So we also wanted to have like a secondary data set which had like very high volume, to kind of like double check all the results that we're getting and just make sure that like what we're doing is like on the right track. And then when actually deciding like which data set to select, our constraints were basically we wanted something that had high volume and something that was biased. So like naturally we kind of like what like has high volume and is biased, and that's kind of like Trump's tweets, in a funny way. So yeah, and yeah, that just helped us kind of like double check our findings and also like do a little bit more research with like a higher volume word embedding.
Justin asked, could this be applied to analyze left-right bias in media publications?
Yeah, so word embeddings in general have just like so many use cases, and that's definitely one of them. You could like create a word embedding and then see like where like given words in an article like land in that word embedding and see whether it lands towards like a politically right view or left view. And in a way, we're kind of doing that for like resumes and gender. So instead of like checking words and see where they land politically, we're just checking words to see where they land like on like a gender scale. But yeah, this could definitely be applied to left and right bias in media publications. And then also another like potential project is trying to like debias that and like, yeah, see how well you could debias something like that.
I just want to mention quickly, there was one part of our project that was cut for time, since we were under some time constraint. So I'll go briefly over it now, because it's what I worked on and I want to make sure it's mentioned. So beyond actually debiasing these embeddings, we also use these embeddings to scan the resume data sets. And sorry, one sec. We use these embeddings to scan the resume datasets that we were given to rank each resume based on a certain set of target keywords that an employer might be looking for. So for example, we chose the target keyword leader because being a leader is good. And then we decided to compare how the resume word embedding versus the Trump word embedding ranked resumes of males and females on their similarity or propensity to be a leader. And what we found based on that was that the word embedding based on resumes was slightly biased towards females, meaning females were more likely to be ranked as leaders. And Trump's embedding was more neutral. So I just want to put that out there.
Yeah, and then to expand on that more, yeah, so one thing that we did find is that the resume one in like some aspects was like more biased. And that's also kind of why like we wanted other data sets to back it up with, because like just the small size of the data set led to a lot of just random variation, which led to like unfortunate bias. So yeah, actually having, because generally these word embeddings are trained on like thousands upon thousands of like articles and news sources. So yeah, for our project group, we like really explored kind of the drawbacks of like having different sized data sets and like what was available.
I have a quick question for you. So we had an ML Fairness project a year ago that was sort of 1.0. This is ML Fairness 2.0. What direction do you think would be good to explore for the ML Fairness 3.0 project at some point in the future? Like, what else are you interested in looking at how we can mitigate bias in?
Yeah, I think the adversarial debiasing was really interesting because it's like super recent. It's only been really used in natural language processing in the last year or two. So it's really difficult for us to kind of gain information and implement that. But if someone were to create a third iteration of this project in like a year, or possibly even a semester, with how like fast machine learning research gets done, like they could probably like explore that a bit more and like create something which is really cool.
Cool. So I guess to close off, I wanted to thank our 2020 e-board. So Ted and Armand are VPs of projects. Shannon, sorry, I think it says projects here, but fellowship, you can be projects. Roger curriculum, Eric for operations. And of course, you want to thank our wonderful advisor, Bistra Dilkina, who's also on the slide. Stop sharing now. Cool, and also, yeah, thanks so much for coming to Showcase. I think Shannon has some extra links and information for everyone here. I think a lot of people here are in the club, but there's some people who are not that could definitely get involved.
Yeah, so we just wanted to mention a couple of things. So if you were interested in our viral genomics projects or climate change projects, those are going to be continuing on into the future. So if you'd like to hear more about them and hear like an update after next semester, please feel free to come to our project showcase in the spring, and you can hear more updates on those. And I will post a link about Computer Science 499 in the chat in just a second. So if you're interested in that, check it out. It's a really cool class from everything I've heard. Have yet to take it, but will one of these days. And then if you're not a member of CAIS++ but want to be, or are just interested in seeing some of the other things we do, please take a look on our website at caisplus.usc.edu for more information about how to join or to hear about some of our past projects and watch our last semester's showcase if you're interested. Yeah, and thank you everyone for coming to this. It means a lot. And we hope to see you soon.
Yeah, and we'll stick around if anyone has any more questions.
Yeah. Before everyone goes, though, huge shout out to Lena. She's been doing an awesome job with our whole club forward through COVID, because I know it's been really hard, but she's doing an awesome job and deserves a shout out for keeping us off the ground this semester.